We now discuss the solution of a problem from the section Linear Algebra, and the problem is based on the concepts of row space, column space and null space of the 4x4 matrices with real entries. This question has appeared in CSIR National Eligibility Test held on 16th February 2022, and this problem is from the section B. The problem is, consider the following two statements. Statement 1. There exists a matrix capital N belongs to M4 over R such that the set consisting of 4 tuples 1, 1, 1, minus 1, comma, the second 4 tuple is 1, minus 1, 1, 1 is a basis of the row space of N, and 1, 2, 1, 4 belongs to the null space of N. This 1, 2, 1, 4 must be a column vector. There should be a T. 1, 2, 1, 4 transpose. Statement 2. There exists a matrix M belongs to M4 over R such that the set consisting of the column vectors 1, 1, 1, 0 transpose minus, comma, 1, 0, 1, 1 transpose is a basis of the column space of M, and the column vectors 1, 1, 1, 1 transpose and 1, 0, 1, 0 transpose belongs to the null space of M. Which of the following statements is true? We are given 4 options. Option 1. Statement 1 is false and statement 2 is true. Option 2. Statement 1 is true and statement 2 is false. Option 3. Both statement 1 and statement 2 are false. Option 4. Both statement 1 and statement 2 are true. So we have to decide, the truth of these two statements. Say, the first statement says, there exists a matrix N belongs to M4 over R such that these two row vectors is a basis for the row space of N, and the column vector 1, 2, 1, 4 transpose belongs to the null space of N. Do we have such a matrix N? And option 2 says, do we have a matrix M belongs to M4 over R such that these two column vectors is a basis of the column space of M, and these two column vectors belongs to the null space of M. Do we have such a matrix M? We shall now discuss the solution of this problem in detail. Now, without loss of generality, we can assume a matrix capital N belongs to M4 over R such that these two row vectors is a basis of the row space of N can be taken as. So, these two vectors is a basis for row space of N. So, we take those two vectors as the first row, second row, and the third and fourth rows are the linear combinations of this first and second rows. So, where the third and fourth rows are the linear combinations of first and second rows. And then if you see the row space of this matrix, these two are linearly independent, and these depend on the above 2. So therefore, the row space is generated by these two vectors and they are linearly independent, and it is a basis for that. And do we have such a matrix? So such a matrix can be taken as this without loss of generality. And 1 to 1 4 transpose must belong to the null space of n. That means the n into the column vector 1 to 1 4 transpose is the 0 column vector 0 0 0 transpose. Multiply. So the n is written here, and 1 to 1 4 transpose is written as a column vector 1 to 1 4 like this, and multiply. When you multiply, after multiplication you get this, and after simplification you will get the column vector 0 4 and star star something. But this is not equal to 0 0 0 0 because this vector belongs to the null space of n, means n times of that column vector must be the 0 vector, but it is not. So this shows that there does not exist such a matrix n belongs to M4 over R such that these two row vectors is a basis for the row space of n, and this column vector 1 to 1 4 transpose belongs to null space of n. Such a matrix doesn't exist. So therefore, the statement 1 is false. Let's look at the next statement in the next slide. So, without loss of generality, a matrix M belongs to M4 over R such that these two column vectors is a basis of column space of M. So, such a matrix without loss of generality can be taken as M is equal to the first column is 1 1 0 transpose, the second column 1 0 1 1 transpose, and this is a basis. And any other column is a linear combination, that is the third and fourth column are linear combinations of the first and second columns. So here it is written third column is alpha times the first column plus beta times the second column, and the fourth column is gamma times the first column plus delta times the second column. So where the third and fourth columns are the linear combinations of the first and second columns, say alpha times the first column plus beta times the second column, that is the third column, and gamma times the first column plus delta times the second column is the fourth column. So that's what the M. Now it is given 1 1 1 transpose, the column vector belongs to the null space of M. Therefore, M into that column vector 1 1 1 1 1 is equal to the column vector 0 0 0, and is also given 1 0 1 0 transpose, this column vector belongs to the null space of M. That means M multiplied by the column vector 1 0 1 0 is equal to the column vector 0 0 0. Right? Let's write down these things. The M times, this is M times the 1 1 1 transpose, that is column vector 1 1, that is 0 0 0 0, that is column vector. And the second one is M times, this is M times 1 0 1 0 transpose, means 1 0 1 0 column vector is equal to 0 0 0 column vector. We continue in the next slide. So this is what we have written there, and multiply. First we multiply these things. If you multiply, you will get 1 plus, these are all 1 1 1, 1 times of first column plus 1 times of second column plus 1 times of third column plus 1 times of the fourth column. So when you do that, 1 plus 1, alpha plus beta plus gamma plus delta, that is 2 plus alpha plus beta plus gamma plus delta is equal to 0, and the second row multiplied by the column vector, this is 1 plus alpha plus gamma is equal to 0, and the third row multiplied by the column vector, then you will get same as the 2 plus alpha plus beta plus gamma plus delta is equal to 0, which is already there. And the third row multiplied by the column vector, you will get 1 plus beta plus delta is equal to 0. And in a similar fashion, we do it here, and we will get first row multiplied by the column vector 1 0 1 0 is 1 plus alpha plus beta is equal to 0, and second row multiplied by column vector is 1 plus alpha is equal to 0, and when you multiply the third row with the column vector, same as 1 plus alpha plus beta is equal to 0, which we have already written, and the fourth row multiplied by the column vector, you will get beta is equal to 0. Now solving, beta is equal to 0, alpha is equal to minus 1. So if you solve, you will get beta is equal to 0, alpha is equal to minus 1. Take these values and substitute here. What happens? Alpha is equal to minus 1, beta is equal to 0. What you get is gamma is equal to 0. How? Take the this equation, second equation, and alpha is equal to minus 1. Substitute minus 1 plus 1 is 0. Gamma is equal to 0. Similarly, delta is equal to minus 1. So you get alpha, beta, gamma, delta values, and the matrix M will be, this is the matrix, and that is alpha plus beta is minus 1, alpha is minus 1, alpha plus beta is minus 1, beta is 0. So these values, and here gamma plus delta is minus 1, gamma is 0, gamma plus delta is again minus 1, delta is equal to minus 1. So this is the one. So it says there exists such a matrix M. So thus there exists a matrix M belongs to M4 over R such that these two column vectors is a basis of the column space of M, and these two column vectors belongs to the null space of M. Such a matrix exists. So therefore your statement 2 is true. So thus we have proved that the statement 1 is false and the statement 2 is true. So our answer is option 1. In the option 1 we have statement 1 is false and statement 2 is true. So that is the discussion of the solution of the problem from the section linear algebra. I am sure that you have understood the solution of this problem, and go on working out some more problems of this type from a standard textbook. I wish you all the best. Thank you.